All right. Good day, everyone. It's 1:01. So we are 60 seconds past the due time. I see you're coming, which is good, reassuring, which means not a lot of you were offended or bored yesterday, which is good. Time to resume, and I'll do that as soon as I'm given control of the screen. Excellent. The screen is coming back to me. And hopefully you see the slides on the screen. If you don't, shout and we can see. No, not shout. Shout on the chat. Don't shout on the microphone because nobody can hear you then. You see that yesterday we did the basics. And I promised the organizers that I should be giving you a short break halfway through today's lecture. If I don't, when you see we are 1 hour 10, more or less, from the start, and I'm not yet giving you a break, you should start rumbling and say, well, what is it doing? Allow for a break. What we do today is we delve into fixed priority scheduling, which I think you understood yesterday is my favorite, not favorite because, you know, soccer fan type of sentiment, but because I believe it's the one that is needed for a lot of reasons. Some of the reasons I hope I'll be able to explain today. And when we transition tomorrow in the world of today, which is multi-core systems, multi-core processor systems, and mixed criticality systems, then I have even more reasons to believe that this would have to be the way to go. You see that I'm using red for some of the parts, and the reason for me using red is to mark the fact that today I will not be able to cover in the oral lecture some of the material, the one, of course, put in red, but it is in the PDF that has been made available to you because the time is too short for my blathering and talking and all of that. So I will be skipping over those parts, but the material is available for you to use. And if you are wanting to come back to me with questions, especially on the exercises and on the detail that I've omitted of the implementation part of this story, I'll be very happy to consider your questions and answer them. It's time at this moment to resume a little bit the Q&A session that we had yesterday. You did fire a few. You may still, if you want, you may still fire some of them now. I'll give you a few minutes for firing any more questions, but there were two in particular, in fact, but I think I should be using as latching point for today's talk. So one of you, a name not given, was asking the question, can you please explain where do we get the deadline, the period, the worst case execution time? You told us that every task and then every job has such parameters, but you didn't tell us, you didn't make it any clear, where do these parameters come from? And I think that's an important question, but let me try and give you initial hints of an answer, and then we'll see whether the answers complete along the way during my presentation. When I tell students in class, when I see their faces and I enjoy observing their astonishment, when I speak about real-time systems, I'll normally tell them that in a real-time system project, in fact, we are having like a caste system, you know, in which at the top there are control physicists. They decide. They know all except for worst case execution time. So they decide what is the sampling time. And the sampling time, you remember the three actions made by any control system: sensing, computing, actuating. So control physicists tell you, look, man, These are the periods, because you'll have to sample at those periods. So periods you don't decide as a computer scientist, as a programmer. They decide and they tell you. Deadlines, they don't quite care, because their notion of deadline is an implicit deadline, which is in fact equivalent to say, you, as long as you're able to complete the cycle, sample, compute, actuate within the period, we're happy, we're satisfied. And therefore, they don't give you deadlines, they only give you periods. But you have implicit deadlines if you want. Otherwise, you can use constraint deadline if you feel that helps your design. So what is remaining is the worst case execution time of jobs. And that's your problem. Control physicists don't care. They want you to fit it. And in fact, they don't care even if you're using clock-driven scheduling, which I consider ludicrous. You don't. They say, do what you like. I don't care. I just don't want jitter. And I want you to respect the period. Okay? The rest, it's your choice. So where do we get the worst case execution time? That is a big challenge. And that's one of the topics that we're going to discuss today. And that's not the control physicist. It's us. It's us where to find it. All right? So this is where I will be elaborating a little bit, and you'll see this is the only place in which there is a role of computer science and computer scientists. All right, so that was one of the questions that I think it was interesting to get back to. There was another question, but and that one we'll also speak about today, and it is, but the scheduler, assume that we know what the scheduler is, because for now we've only been speaking about scheduling algorithms. The scheduler, so the entity that does the scheduling, is it aware? Does it understand that it is costing, that it is taking time? Or it is unaware of that? So does the job of scheduling, or does the activity, so that you don't confuse the notion of job, disregarding the fact that all that it does is costly. And we'll get back to this. So that's an important concern to have. And again, as part of today's lecture, we should be touching on that topic, and we'll even have a poll on that particular argument after I'm giving you a little bit of a background on that. So these were two leftover questions from yesterday. And unless you have anyone in the last 15 seconds, we can start the actual lecture of today. So 14, 12, 10, 8, 6, 4, 2, go. We resume. Very good. And what do we talk about? The proper version of time demand analysis. You may remember, and those who do are good, but yesterday I gave you a little bit of, of a notion of economics to say, how do we decide that the system is feasible when it is scheduled under fixed priority scheduling with preemption? And we know that deadlines are either constrained or implicit. Well, economics was using time demand analysis. That is to say, to assess whether the time available, which is called time supply by the CPU, equals or is never inferior to the time demand. That is all that the existence of jobs issued by tasks would require being present at the release of every such job. Okay. Now, you may remember the step function, which is the representation, a graphical representation of this time demand analysis. But in fact, the most interesting translation of that one was not the full step function. It's the perpendicular of the point of crossing, if any such crossing exists, between the time supply and the time demand, because the projection on the horizontal axis of that intersection point is exactly the response time. And that is the thing that matters. So what are we concerned with is a fixed point equation. And again, now you see that suddenly I'm using C instead of V. Some of you noted yesterday, well, again, you're confusing me because sometimes you're using E, sometimes you're using C. It's not me. It's a community which is multilingual. And sometimes you're using E for execution, and sometimes they're using C for computation. I am ambivalent, you know. I have opinions on clock-driven scheduling, but I don't have opinion on this one. And therefore, I'm happy that, you know, I'm using whatever fits the day, and I apologize in advance if it is confusing to you. Now look at this fixed point equation. I think we understood yesterday that this equation it says the point of equilibrium, if any such point exists, between the time available, which is this side of the equation, and the demand of time by the tasks executing under fixed priority scheduling is in fact the right side of it. So this demand is what the job needs to execute at its maximum demand for that particular job, plus this term, which is in fact the definition of interference. That is to say, the time that a job scheduled under fixed priority scheduling suffers, is held, that cannot get to a CPU because other jobs of higher priority than itself are in the queue and they will have to execute ahead of time. So that's all the equation says. And it says these jobs of higher priority will execute with their maximum demand as long as that window is open. That is to say, as long as they are in the ready queue. Okay. So this equation, this fixed point equation, finds a point of equilibrium only at the point in which the time supply is sufficient to accommodate all of the time demand. Okay. Solving this equation is not too difficult. In fact, it's a simple recurrence relation. You start with the initial value of this window, which of course can never be smaller than this amount. And then you start seeing when it converges. In the slides, there is an example, but I'm skipping it orally. The interesting part of this equation, so please allow me and do not really reproach me for skipping the example of use. It's sufficiently simple, but if you look at the PDF of the slides, you'll be able to make sense of it. The most important part of this equation is that you know exactly the worst case interference. And I believe that for real-time scheduling, this is a super important information. So when you design a system, you want to know how much will I suffer because of the presence of interference people. Interference, not people, but tasks. And you know, with this equation, you know that exactly. It says, look back here, it says you will suffer interference, which is upper bounded. It will never be less than this amount. And of course, as long as this window increases, you suffer more interference. Okay, but you know this bound. And you know this bound by design. And I believe this is super nice. Not because this bound is small. This bound may be very large. But knowing it in advance is very reassuring. Is really what helps you. Okay. Now I'm skipping. You notice a jump. You know, I've been making one of the many jumps I've been making today. I'm jumping from 89 to 91. This is a small leap, but never mind. Huh? And I'm trying to go closer to reality from theory. You remember that I told you that deadlines and therefore tasks are classified into hard, soft, and firm. Now, who is giving this classification? Control physicists? Never. To them, everything is equally important. Because it's their thinking, it's their equations, you know, it's sensing, computing, actuating, so everything is equally important. Who is deciding what is hard and is soft? In fact, it is your judgment within limits, because you have to downgrade to soft what is in the judgment of these people, in fact, entirely hard. So in reality, a real-time system has a coexistence of hard tasks, which means they have hard deadlines that can never be sort of missed, and soft deadlines. The tasks that, you know, you're happier if they complete in time, but occasionally they may be a little late. Notice that when I'm saying they may be a little late, this will be very dangerous for EDF, because in EDF, when somebody is late, becomes important. And when somebody late becomes important, everybody else is delayed by that stupidity. So in this case, instead, having soft deadline task is more gently treated. But in a real-time system, in reality, you have both. And now this is a problem because you have to sort of deal with them and treat them so that the hard tasks are given all guarantees and the soft tasks are given less guarantees, but they still are useful. So you are serving them without leaving them, die in the cellar. And this is easy to say, but more difficult to do. And why is it difficult to do? Because we work on worst case predictions, in particular on the worst case execution time. And as in all things in life, worst case can be much, and many times much worse than the average case. So you may have an activity, a main procedure from beginning to end, which really oftentimes is taking a very little time. It does something very linear, there is no else. It does only the then part. And there are occasional situations in which it does all of the ramification, goes nesting into this particular loop and all of that, and it takes much longer. Well, our analysis, our design contemplates the worst case. It doesn't help that the average case is 100 times smaller. What matters is that the worst case is 100 times bigger. Okay. So that's a problem, because if everyone comes with worst case demands, then somebody will suffer, most likely. And we have to reflect on who suffers, because that's a decision you have to make. It's easy enough at design level to make such a decision with fixed priority scheduling. And this is a rule of thumb. It's not really something that is in a theory book. It is more like in a handbook of the practical engineer for the real-time system. And it says, well, first of all, try and reason average case. Oh, average case. You told us many times, you don't consider average case. This is the beginning of a rule. You try and see whether the average case execution times for all tasks, hard and soft, meet their deadlines. And you want to be able to say yes, not a politician's yes, a true yes. And if it happens, you say, all right, so at least I know that if they behave average, everybody's happy. Of course, not everyone and not always they behave average. Some behave worst case. When that happens, we have a transient overload, a situation which is not permanent, has a certain lapse of duration in which not everyone can fit. And this is where Rule 2 come into the picture, and it says in that particular case, those who have to be feasible, but they have to be satisfiable with worst case demand are the hard tasks, and as many soft tasks as you can fit. You understand? And therefore, the leftover is soft tasks that you say, I'm sorry, man, I give you a lower priority, and you suffer in case of a transient overload. Okay, so this is roughly the logic of it. And it's the nice part of this story is that it can be reasoned about at design time, which is quite okay, because that's what you want to do. At design time, you want to be able to reason. And now we make one step more. We go into a very difficult territory. And you see, I'm breaking my own stipulations, because I'm now, look at the title of the slide, handling aperiodic tasks. And I gave you all of the story yesterday in the opening, which I'm saying now, we can only handle periodic tasks. And now I'm saying like government saying, well, I will lower taxes. And I say, no, sorry, I cannot really. Yeah? Now, why would I want to include and handle? Now you see, I'm missing an L, handing. I don't want to handy. I want to handle. Apologies for missing an L here. We want to handle aperiodic tasks. Why? Because aperiodic tasks, if we find a way of accommodating them in a real-time schedule, they may deliver useful value. The typical example I gave students to believe that aperiodic activities can be useful is this. No? Imagine you are on a fixed employment, on a fixed salary, and that salary is very low. And you say, gosh, I want to earn more. So what do you want to do? You say, I want to become a rider, and I deliver, food at home in this period of, home confinement. Now, if you deliver home stuff, food or other things, then you get an immediate income. Whereas if you work on a fixed salary, you get salary once per month. Okay, so the fixed salary is periodic, period 1 month. Your ride delivering at home is paid, if you believe it so, I don't know, but I presume so, you're paid per delivery. What would you rather do? Deliver when you have free time from your job, free fixed salary job, or deliver as soon as there is a demand, and then you work harder and later at your fixed job. Because if you deliver as demanded, you get paid immediately and you earn more. And I think the answer is obvious. Hopefully I made it very clear. So this home delivery by the rider is an aperiodic job. You do as required, but there is value in doing it as soon as possible. There is much less value in doing it later. You understand what I'm saying? Therefore, the requirement is, if you want to contemplate a periodic task, the only way to do it is to serve them as soon as possible, because otherwise they are not as precious, okay? But they are aperiodic, so you cannot really give them time, because they would have no demand. They are totally undisciplined, they are hooligans. When they come, they come. Therefore, you have to find a way of treating them. How did we handle them in cyclic clock-driven scheduling? Well, we said, I was very brief on that moment. I said, well, we take the schedule, which is fixed. We find the holes, which is the white in the timeline. We shift, if we can, those who are scheduled earlier, and we move the white, the empty, earlier. This is called slack stealing. And then, however, that amount is fixed in a clock-driven scheduling. And if anything happens in that moment, okay, I deliver. If it happens later, say, I'm sorry, man, I can't attend because I'm working fixed time. Can we do any such thing for fixed priority scheduling? The answer is no, it's very difficult. Let me explain you why. Because calculating the slack for fixed priority scheduling is not immediate. It's a function of time. In cyclic scheduling, clock-driven, it's static. It's computed once and for all. In online scheduling, it's not computed once and for all. It is a function of time. And therefore, you would have to have someone that during execution determines if the actual slack is sufficient to accommodate some, rider, a periodic job to perform. And then you have to trust these hooligans that tell you the truth. You say, well, I'm only executing this much. But they don't tell you the truth ever, because periodic tasks. So when you take a home delivery order and a rider goes, he asks, where is this address? Is it close? And of course, the owner says, of course, come on, it's near the corner. And when you go and it is in Oklahoma, it is not that close. So that is difficult, complicated, and of course, in principle, looking at timelines, you can determine, and this example shows, but again, I'm not commenting on it, but you can determine what that is soundly. But again, even if I were able to calculate that on a timeline statically, I would only know the maximum quantity. I would not know the actual quantity, because it may be slightly greater than that. So it's complicated. It's complicated for EDF. It is complicated for FPS. And therefore, slack stealing for fixed priority scheduling is not really the option. Never was. It was studied. The conclusion was that we can't really find a proper solution. There were publications, important publications, that explain what was possible and what was not possible. And in fact, what was not possible was much more than what was possible with them. Therefore, not really the way to go. So there must have been another solution. And the other solution is to have a different scheduler for the aperiodic tasks. So imagine now it's like saying that we're having two schedulers. One that schedule the normal stuff, the periodic tasks, and the sporadic task, assuming that any such thing exists in reality. And then we have to invent something else that is the rider or the owner of the drivers, riders, not the drivers, the owner of the riders who deliver food at home. And this we call, first name that was given to it is in fact periodic server. The periodic server is in fact the personification of a task which is scheduled by the normal scheduler, but the job of his task is not to execute itself. The job of his task is to give time for the execution of periodic tasks that come in. Okay? So that's the job. And what does this server do? It is a strange fellow because it has a period, so it is periodic, and that period is called replenishment period. That is to say, at every arrival of a period, this particular task, which is a periodic server, reacquires fully a budget, which can spend during one period, giving time for the execution of a periodic task that become. If the periodic tasks want to spend more, they have no budget, and therefore they don't execute more. If they spend less, everybody is happier, because then the interference caused by this periodic server on others is less important, and therefore that's a way. So that's why you understand we're having a two-level scheduler, the scheduler of tasks, and then a scheduler of the periodic tasks embedded in what seems like a task to a primary scheduler. Okay, is no this solution what is used today? The answer is no. Why? Well, because it is naive. This thing is too naive because it does replenishment blindly. Okay, and that doesn't look like very interesting. Okay, but before telling you what was the remedy to the naivety of this periodic server, I'm giving you another approach that was proposed, and luckily it went, finished on a book and then never used. It's called polling server. You know that when you mention polling to real-time systems, people, they start running away. They say, oh, the devil, the devil. Polling is stupid. Well, again, some people will say, don't say this is stupid. Yes, polling is stupid because it's like, imagine that you're sharing a phone and your friend is using your phone and you need to call you on that phone. Then you want to know whether your friend has finished. What is it that you wouldn't do if you were intelligent? Well, you wouldn't tell your friend, please give me the phone, because if he answers you, he's not finishing the conversation. You understand? So polling is not useful because polling asks, are you done? Are you ready? Anything to do? And that's not useful because when you ask, nothing happens, but you spend time asking. You understand? So this polling server is like having a task, periodic, but periodically say, a periodic job here? And of course, if there isn't any in that moment, it goes away. But Murphy says, as soon as you ask and the answer is nobody, you close your eyes and there is a long queue. So this is obviously nonsensical. No, nonsensical is too gentle a term. I'm calling it stupid, and please allow me to call it stupid. So what do we do? Well, the defect of a periodic server is that it is replenishing regardless. So it may spend budget for the periodic tasks. It may not spend budget for the periodic tasks, but it is replenished nonetheless. And people say, well, that's not really what you should be doing. You don't fill the tank if the tank is full. You see what I mean? So you replenish only when you have consumed. So they invented another server, and this is called Deferrable server. And the Deferrable server is that it does what you expect to do. So it keeps the budget. It keeps fuel in the tank if it is not used for executing periodic tasks, and only refills when it is exhausted. And it refills, however, within a certain bound, which is acceptable, if you like, for the quality of the serving of the aperiodic. So that's roughly the logic of it. So you say the key feature of this particular service style is that it does not throw the budget away just to refill, but it keeps it. Whenever an aperiodic task arrives knocking on the door wanting to execute, if there is budget, well, it is considered within the period, and then it replenishes only when it is exhausted, if it ever becomes exhausted. Now, is this good? Unfortunately, it isn't. There is a little bit of a glitch in the logic of this particular server. And the glitch is that the promise of a deferrable server is that the interference it causes to the other tasks is bounded. What I'm saying to the other tasks is to the task that happen to have a lower priority than this deferrable server. But now consider a situation in which this guy is still having a little bit of budget near the period of replenishment. Is exhausting its budget, and it is all pushing the service of a periodic until the end of its period. Period comes, it is replenished, and has a queue with more aperiodic, and therefore continues serving them. Now, from the perspective of a lower priority task, they are not happy, because now the interference that they suffer across two periods is longer, because it is a continuum that spreads across the period before, in which it was pushed near the end serving, and it resumes interfering after it is replenished. So that in that case, if you want, the Anthony Fauci would say it's premature replenishment still, okay? But Trump would not understand the explanation. So what was invented is a sporadic server. Sporadic server, which is much more complex in rules, is able to replenish so that the interference caused is as bounded. It is not exceeding, not even by a small epsilon, okay? But of course, as all things that are sophisticated, the rules are complicated. And in fact, they were so complicated when it was the first ever implementation in any standard, if like real-time platform existing, early 90s, it was an erroneous implementation. So it was too complex to translate into code, and therefore the theory said this is what you do, and the practice was that the implementation was not doing what it had to do. If you're curious about the sporadic server, so this SS, don't think of anything history, Second World War, doesn't mean that, it means sporadic server. Read the slides, and if you have any questions, feel fire them to me happily. So what is the conclusion for this? Is that there are ways to serve aperiodic tasks, okay? Which is good news, because aperiodic tasks are hooligans, but if you behave them as the Brits were able to do with all of the cameras and all of the tribunals and prison and whatever, then they deliver value. And there are solutions, as I mentioned, for fixed priority scheduling. And there are equivalent solutions for dynamic scheduling with, like EDF and LLF, which I will not mention. They are similar in notion, but they go under the notion of, dynamic priorities for jobs or dynamic priority for tasks, which are more complex, if you like to consider. Now, this is a time at which I would like to make the first poll for today. So please be more responsive. Yesterday, the record of respondents to poll was 94, which is a good number, but I would like to reach above that number today. So the first poll for today has this title. Let's see if I'm displaying the poll to you. What I would like you to do is to tell me ahead of time whether anything important is missing. So now we're able to handle sporadic tasks in some way, periodic tasks, and now I've given you a way to believe, if you believe it, that we can handle also aperiodic tasks. So the question is that all? Are we covering all real-world needs, or anything is missing? Here is the poll, you see it. Consider the questions, read them, And then, 20 seconds from now, please start responding so that I can see what you think. All right, responses are coming. All right. Come on, come on, come on. We have to reach 94 at least. More, please. More. Voting is slowing down, which means too difficult questions. Hopefully not. Yeah, come on, make an effort. 56 seconds, 57, 1 minute, 10 more seconds. I might have to say, come on, guys, who did not respond. Yep. Who are you are using web browser? Don't use web browser with Zoom. 120. And Paul, gosh, not enough answers, but never mind. Let me show you the result. I'm sharing the result. So now the majority, which is not overwhelming, but it is, a majority says, well, I believe there is more. I believe that the real world is more complex than we currently can handle. And I think that's inkling in the right direction. The real world is indeed more complex. And most of all, it is absolutely impossible that tasks are independent of one another. Not only for ontological reasons, because tasks, as I describe them, not because I have authority, but because that's the way they are. Tasks are there for architectural collaboration. So when saying that tasks are independent, it means like collaboration, they don't collaborate. So that's not what it is. It doesn't mean that all tasks collaborate with all tasks, but collaboration is there, and therefore only considering and assuming that tasks are independent is an impossibility. It's absolutely impossible. And one answer says, oh man, you lost me. We have been speaking for 3 hours almost, and I didn't really find myself in any direction, so which is a critique of this particular lecture. All right, let us resume. So now, of course, if I were consistent, and hopefully I am, but we never know, is that we see what we can do about lifting this restriction of tasks being independent. So what do we want to do? We allow tasks to interact. But let us reflect. How can tasks interact? Interact means collaborate. What is their way of collaborating? How can they collaborate? Well, before I speak about preemption, which is a key to it, well, they only collaborate by sharing data. Well, sharing data is already hinting at a possible solution. If you are a purist, you would say, no, tasks can send messages. So that I have something to tell you, I send the message to you, and you receive my message, and you do what you want with it. I think it's easy to have the intuition that exchanging messages in a real-time task is nonsense. Because real-time tasks cannot just wait for others to send message, because that wait time can be completely unbounded, There is a beautiful book, out of many beautiful books, by Gabriel Garcia Marquez. The title of that novel is Nobody Writes to the Colonel. Imagine you have this colonel in the jungle waiting for letters that never come. This can never be a real-time colonel, evidently, no? So message passing real time for verboten cannot be had. We don't use it. So what's left? Data sharing. But data sharing is very dangerous because there is preemption, not because of data sharing. There is preemption because of scheduling. So imagine what happens if you are sharing variables or data structures and you are preempting. So this is the most important instance situation in which you understand that you want to preempt tasks and the execution of jobs, but you do not want to preempt resources, share resources, because resources that are owned temporarily by jobs being preempted, they cannot and should not be used by others. Otherwise, they cause a mess. And the example I give students here is as follows. Let me try and give it very, very simply. Imagine that, we are all stuck at home in this period. Hopefully it will finish soon, but, and in this particular family, there is only one desk and there are 2 kids. They have to share the desk for studying. So they found, the 2 kids, one boy and one girl, found a way of sharing the desk, but they have, of course, very different characters. And then, there is a boy who sits and prepares the desk, cleans it up, places all of the books and the notes and the pencils and all of that. And then at some point, the guy gets bored and starts using WhatsApp and walks around the house and goes to the garden. And then the girl says, he's not using the desk, so I'm using it. So she preempts the desk. And if she preempts the desk without the boy having finished, it causes a mess, because when the guy comes back and finds that now what used to be a setup for the desk has been completely moved and destroyed by preemption by the sister, then a row comes and it's a disaster. I think you understand what I'm trying to say. Preemption is fine for tasks. It is not fine for resources, for shared resources, sorry. And therefore one says, all right, so you're telling me that you want preemption because you want to schedule tasks preemptively, but you also tell me that you don't want preemption because you want to share data. So what's the solution? Inhibit preemption when you're sharing data. No? And this is very drastic. But suppose that I like doing it, and I don't. But suppose that I like doing it. So I say, well, okay, I will consider inhibiting preemption. Then I have to understand, how can I do that? And when I ask my students, they are younger than most of you in this webinar, hey guys, how would you inhibit preemption? They wouldn't know. They would look, there must be a button. There must be a button on my laptop that says, if you press this button, no preemption. And there is no such button, and never was. There was never such a button. So preemption occurs because we really fool the processor. We trick it. The processor, as was designed, not really by Turing, but by his mentor and at some point also supervisor, John von Neumann, was never meant to preempt. It was a continuous flow of activity, which we know is now called the pipeline. It's fetch the next instruction, decode the operation code of instruction, retrieve the parameters, elaborate on the parameters, write back to memory the result that are staying in general registers. And this is done all the time. All the time. There is no preemption there. So how is preemption applied? By tricking it, by forcing the fetch, and I'm telling students the F of the fetch, to, before proceeding, asking whether anything happened outside of this execution cycle that required attention. And this is called interrupt. So if any such thing occurred, then you say, well, I will not be fetching the next instruction. I will be doing something else. So that's the notion. That's how preemption occurs. And how can you disable inhibit preemption? By telling the fetch stage, don't look at this. Disregard this request for interrupts. Okay? So you understand the implications. The implication is that if you want to inhibit, first of all, if you want to have interrupts, you fool the fetch stage by having external signals indicate that they want attention, and this would be called an interrupt. And then diverting the activity from the fetch to something else, which we normally call interrupt handling, and which we'll speak about in a moment. And then, resume that afterwards, the normal cycle of operation. Disabling, say, don't listen to interrupts, which may be done by ignoring interrupts, which are just bits asserted in a particular register, or by prohibiting that the bits are asserted in that register. So that's what you do. Okay. So fundamentally, the bottom line, if I was a journalist, I would say, well, I knew that, preemption is a fake, preemption is a lie, preemption is diverting the nature of processors, and in fact it is. The same way as you add it, you can disable it. Now, disabling preemption, is that a nice way for allowing resource sharing without preemption of the data that you're sharing? And again, the example I give students in class about it is like, imagine that I have my grandmother, she wants to cross the street. She presses the button on the traffic light, and if this was working on inhibiting preemption, all traffic lights in the city would go to red for cars, so that my grandmother can safely cross the street she wants to cross. And what would be your reaction, especially if you're a driver? You say, you must be mad. I'm 50 kilometers from your grandmother and you're giving me red light? You must be stupid. Again, stupid. Sorry if I'm saying stupid, but you understand? Say, no, it's impossible. So inhibiting preemption, because Mickey Mouse and Donald Duck want to share data, and there are another 20 tasks that don't want to share anything. It's like, gosh, it's extreme. You understand what I'm saying? So it's a solution, but it is too drastic a solution. And most of all, this solution causes everybody to pay a price. Because if I inhibit preemption, those who can preempt cannot. And for how long? Well, for the maximum duration that a lower priority job grabs a resource and say, don't disturb me. Okay? And this can be very long. So this is not nice, because it sort of undermines severely the higher priority tasks. They say, you gave me a privilege, high priority, and now you're taking it away because you're taking a preemption away from me. So not really nice. Think of something else. Think of something else. And of course, we have to think of something else. And now we start an elaboration. Hopefully, it's interesting. To me, it's always been very fascinating. Hopefully, I'll be able to project the fascinating element of this story. But if I'm not, well, complain. But not now. Complain later. So we have to invent a way, in fact, a protocol. A protocol is an agreement. An agreement between parties. You shall do this, I shall do that in any particular order. And if we do this, then benefit is accrued for both. And this protocol, which is an agreement, regulates access to shared resources. So that's a control protocol for access to shared resources. That's what we want to do. And of course, we want to have a protocol which is intelligent. What intelligent means, it reduces the damage that is given to the general public. Okay? The principal damage that you cannot avoid is that when you compete for access to a shared resource, one grabs it and the other doesn't. The one that doesn't grab it, inevitably in a fixed priority scheduling system, is, if this ever happens, a higher priority job, because it preempts the lower priority job that has the resource and then finds the resource busy. Okay, so this is called direct blocking. Obviously, it happens. So it doesn't happen vice versa, because if a higher priority job acquires a shared resource shared with a lower priority task, then it doesn't care, never sees lower priority tasks. So this direct blocking is when a lower priority task that was running alone with no other interference at the time grabs a resource shared with the higher priority task, and it is preempted as a job by that task, and that task would like to get the resource but should not get it because the resource is non-preemptible. Okay, so you understand that there is a direct relation between the two. Then we would want this blocking, that's a term, to be confined to as few tasks as possible, because otherwise we have a situation analogous to my grandmother crossing the street. So there are various relations of, who is waiting for what resource in principle, but it's not the time to elaborate on that. As I said, the easiest solution is to say, when I acquire a shared resource, I press a button, no preemption, okay? I already described that's not very nice. Can we upper bound how much are we suffering? By the way, the suffering that we have is called priority inversion, because it is a situation in which those with higher privileges are denied their privileges for the sake of keeping resources together. And you want to know what is the worst case. Please give me ahead of time what is the maximum time that I can suffer this blasted priority inversion. And the answer is every job of any task may suffer once per job a blocking, which is a direct blocking, but can be as large as the maximum use of a shared resource by a lower priority task. Notice that when you design a system, if you have a low priority task, you say, well, I'm always interfere with. So when I'm grabbing a resource, I'm using it all, So again, I'm thinking of, when I was a kid living in a family of numerous families with, a single bathroom, and I liked reading, Mickey Mouse in the bathroom. And I said, well, I'm reading. And everybody was knocking on the door. Come on, get out of there, stupid. And because I was giving them a tremendously high priority inversion, because I was saying, oh, come on, you're adults, leave me alone. I'm reading Mickey Mouse. You see what I mean? So the design of a lower priority task may misunderstand the implications, because it is not interfering with the priority task, but it's giving them priority inversion in this technique, which is very bad. So we don't want to use it. This option is very rudimentary, very basic, very drastic, and we don't want to use it because everybody pays. Okay. The important term we have to learn is priority. The term is priority inversion. So we need a cure for this disease. So we look at Anthony Fauci and say, Mr. Doctor Fauci, please give us a vaccine against priority inversion. And Anthony Fauci says, well, man, there is a solution. And the solution is that those who are blocked by priority inversion offer their privilege temporarily to those who block them. And by offering temporarily this privilege, those being preempted but holding the resource can go away earlier. Okay, this is called priority inheritance. So that's a mechanism to say, well, I'm suffering, but because it is my interest that you relinquish the resource as soon as possible, I give you my privilege as long as you use the resource so that you get off earlier. Okay. If this can be organized, that's a way of reducing the blocking. And there are ways of doing it. So the easiest in the sense of the naivest way of doing it is called basic priority inheritance. Of course, the namesake explains. How does it work? Well, look at the rule. The rule is as follows, and it says, well, of course, we are scheduling in fixed priority scheduling. But the rule is, now there is a job running. If it is running, it means it is at the top of a ready queue. So it is running, and while running, it says, I want resource R. Of course, if the resource is free at the time you ask for it, you get it. And you get it until release. It is not, in a real-time system, it is not possible that you grab the resource and go away. You get the resource on a loan and you return it as soon as done. But what happens if the resource is busy when you want it? Now, let's ask ourselves, is it possible that I can be running and the resource I want is not free? Of course it is possible. If I am higher priority than the job that before my preempting had grabbed the resource. So therefore, it is entirely possible. So if that situation happens, I am running, I want resource, and the resource I cannot have because it is busy, then I become blocked. So I'm leaving the ready queue. I'm no longer in the ready queue, but I'm not there voluntarily because I'm not finished. So I'm in a special status called being blocked, okay? But because I'm blocked by definition by a job that has lower priority than me, I can do something for it. And I can give that job my priority. And because I was running at the time, it means at the time, my priority was high enough to run. So presumably, it's high enough for this guy to run. Otherwise, it is preempted normally. So in the principle is that I can give my priority temporarily to this guy who acquires my priority and inherits it. And he uses it to finish the job with R. And as soon as it leaves R, it returns to the priority that it had originally. Okay, this sounds like interesting. Well, nice. Well, sounds like I think I have a story in mind that depicts this situation. Is this a good scheme? It's not the time for a poll, but this is not a good scheme. Sounds clever enough, but it isn't. And the reason why it isn't is that it causes transitive blocking. Why? Well, transitive blocking is that, having acquired one resource and being preempted may lead the task being blocked to give temporarily this benefit of priority inheritance. But this causes no benefit for any other resources that the task giving the priority, the task being blocked, will want in the future. So let me say that again. How many resources may a task need during execution of a job? Well, some people say only one at a time. And then I'm saying, well, try and eat spaghetti with only one fork. When I was young and I was very dexterous, I was eating spaghetti with a single fork. But becoming older, I found that, I was smashing myself all with sauce and all of that. So I said, no, not a single fork. I would need two things, perhaps a spoon. So I need two, fork and a spoon simultaneously. So how many resources do I need for my job when I eat spaghetti? Perhaps two simultaneously. How do I acquire the fork and the spoon with the protocol? Well, I am fighting for the fork. I may be blocked requesting the fork. Finally, I may get the fork. Does this tell anything good about when I want the spoon? And the answer is no, it tells nothing, because of course even the spoon may be taken by somebody else. So I've been blocked on request for the fork. I will be blocked on request for the spoon twice and then 3 times. So this protocol doesn't help. And this is even worse, because if you have this transitive mechanism of direct blocking and you allow accumulating multiple resources, then of course you expose yourself to deadlock. Deadlock is when I am grabbing the fork and then the spoon, and my neighbor grabs the spoon and then the fork. And this is damaging. Of course, if we were in Germany, we would put rules and say, you always grab the fork first and the spoon second. Of course, if you give total order on the resources, then you have no blocking. But you are in the Southern Europe, and you are not a frugal country. You say, well, grab what you want, You're left-handed, this way, that way. But if you do that together with a frugal countryman, then there is a problem and deadlock occurs. So this protocol, is it nice? No, it's not. Are we going to use it? No, we are not. Anybody using it? Yes, Java. Can we call Java real time? Forget it. So that protocol was one step ahead of, just inhibiting preemption, but it is not many steps ahead in reality because it has important flaws. So there was the need to look for something better. And the better is, Can we find a way of not suffering from this disease? And again, Anthony Fauci comes and says, yes, man, I have a solution. And the solution is complicated, but let me explain. And of course, he doesn't talk to Trump because he doesn't understand that, but he talks to the other people. And what do? They do the following, say, well, imagine now that we add a control variable in the application controlled by the real-time operating system. And this control variable, we call it system ceiling. The system ceiling monitors and becomes equal to an attribute which is attached to every shared resource. What is the attribute attached to every shared resource? It is called priority ceiling. And this priority ceiling is statically, mind this term, statically attached to a shared resource as the highest priority of the tasks that may want to use that resource. So imagine that you have a use graph. You have a resource there, and then you have arrows of use. Okay? Each user, which is not simultaneous, but it's a potential user in the system lifetime as a priority, as in all fixed priority scheduling systems. So now the resource, which has this many users, says, oh, I have a priority ceiling attribute, and now the way I compute it is the max priority of my user tasks. Okay, so every resource has this attribute statically. The system has an attribute called system ceiling. And the system ceiling monitors what is the highest priority ceiling of the resources currently used. So initially, there is no use, therefore it has a bottom value. And then the first resource is being used and say, oh, right, okay, so what's the priority ceiling of this resource which is currently in use? Well, it's this ceiling. All right, so now system ceiling takes that value. Then something else happens, preemption, boom, 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 boom. This other task arrives, gets another resource, and the ceiling of that resource is higher. System ceiling goes higher. That resource is released, system ceiling goes down. So this variable requires certain activity, but still tells what is the system ceiling value. What's the use of this system ceiling value? It's an important use because now the following happens. Hold on a second, I'm having an alarm. Apologies, 30 seconds and come back. Apologies, it's not the time for questions, it's not the time for poll, but I had this alarm and I was alone to handle it. So let me resume. So I was saying, we're having this system ceiling, and the system ceiling is clever because it helps deciding whether you want to give resources or not to avoid situations that may be dangerous, including deadlock. How do they operate? Well, when a job is running and wants to acquire a resource, we check again, is the resource free? Because of course, if it is taken already, it is as before. You're blocked and you inherit. But the tricky part, the interesting one comes, if the resource that you want is free. Well, if the resource you want is free, this protocol says, well, be careful, be careful. Perhaps you don't want to give the resource, even though it is free. Because if you give it, perhaps this resource may be used in the near future, or rather, sorry, it's not this resource, but something else that you may want is already taken, and you will not be able to get it while holding this resource. So let me again try and elaborate on this particular clause, which is really very tricky, but also very clever. It says, now I'm having the system ceiling. The system ceiling tells me what is the highest priority ceiling of all of the resources currently in use. All right. Now imagine that my priority, task, job priority, of me wanting this particular resource being lower than the system ceiling. What does it mean? It means that there are resources currently in use wanted by tasks of priority greater than me, wanted by, but held by somebody else. You understand? So can you see the feel? That's a situation which is strange, because there are resources that I may want, because their priority ceiling is either my level or even higher, so I may want them, that are held. So even if I continue running, I will not be able to have them because they are held. So there is only one safe condition for me to obtain this resource, which is free. And that condition is that this ceiling priority is lower than my priority, because it means at that time, no resources that I can care for are busy. So the fork is free and the spoon is free, and I can get them. And then you may object, saying, oh no, man, you are tricking me. What if you are preempted? And then I'm telling you, if I'm preempted, no problem, because preemption I never see. You understand? Blocking by resource sharing is the opposite of preemption. Preemption I never see. I am preempted, but I don't realize. Because a guy that preempts me comes and they go. And when they go, I resume. I don't understand. I don't see this happen. It happens, of course, because the clock runs, but I don't see it. With blocking by resource sharing, I do see it because I'm running, but I cannot continue. You understand? So it's very important that you are given a resource in a condition which you can continue running. Otherwise, it's hopeless. You may end up in deadlock. Okay? So that's the purpose of this system ceiling, which is very interesting. Of course, you begin to see that there is a full page of clauses. It means, wow, this begins to be complicated and sophisticated. So I'm using a system ceiling value, which I have to monitor all the time. But the benefit is that I am giving resources in a manner that avoids deadlock. Not only that, it has an additional property. And let me, of course, I'm adding now one particular blocking, because first we had direct blocking. Say, I want resource, and the resource is busy. So I have, this guy is blocking me. Then we're having inheritance causing another blocking, because now I'm donating my priority so that the guy that is lower priority is temporarily able to, preempt me, or rather preempt, not allow me to continue. So that's a sort of blocking called inheritance blocking. And now there is a third type of blocking with this protocol that says the resource is free, but you cannot get it, because if you get it, may be dangerous, and we don't want danger. So that's a third form of blocking. So indeed, it is more complicated, but this additional blocking has two important properties. The first important property is that in this manner there can be no deadlock. So now when I explain this to students, and they often come to class for this particular topic, after they go to a class of a colleague who elaborates on software verification and abstract algebras, and where they spend hours and hours and hours of finding deadlock. And I'm telling them, look, in my domain, we have ways of preventing deadlock by design. So we don't, not even if we try, we have deadlock. Okay? Which I think is a good thing. And the cost of this protocol is, perhaps a price to pay. But there is an additional benefit, and this benefit is another super important. It has been proven in a theorem by these guys in 1990. This is what this theorem says. If you are using this protocol, we can tell you ahead of time that any job sharing resource may be blocked only once, a job blocked only once for one use of a critical section, that is to say, the use of a shared resource. Only once. With a previous protocol called priority inheritance, how many times am I blocked? And the answer was every time I want a resource. So my total blocking time, including the risk of deadlock, is a summation. Not very nice. This one says you only pay this price once at most. And when do you sort of pay this price? This says you pay this price when you want a resource, fundamentally, but only once, okay, and not all the time. So in the worst case is that duration. So there is a way of calculating it. I'm not really explaining it. If you're curious to see how you calculate it, you try and decipher this slide. But the most important, and then of course there is an explanation so you can make sense of that and you not really think bad of me. Is that protocol good? Well, it sounds like good. But then a friend of mine who is retired, is a very nice fellow, very humble, very timid, but very intelligent. His name is Theodore Baker, TED for Friends. I was allowed to call him TED at some point. Came back with an observation, said, that protocol is disastrous. Does very big damage when the tasks share the stack. And then you wonder, would tasks share the stack? Now let's reflect on this. Those of you who have an interest in the programming part, in the implementation part of real-time systems, should have an opinion about it. Should tasks, let us go in order. Do tasks have their own stack? Well, the answer is, of course they have to. Of course they have to. Because a task is a main procedure, and they may call procedures from the beginning to the end. And you don't want the data in the procedure call to be spoiled by preemption. Therefore, you want the stack to be used per task. Then you want to say, but in a real-time embedded system, can I possibly have one task per stack? Notice, you have to have a stack per task. But you say, can I have just a single task per task? And then you say, oh man, but then I have to give every such task the worst case size. And then I'm summing all of the worst case sizes for all of the stacks of all of the tasks. And the result is that my RAM is exhausted and I cannot have it. And therefore, you need to look at somebody that is more, implementation able than you. And these people say, well, you can really try and imagine, and you see that you can share the stack among tasks. And if you do share it, the worst case size is the same, but the average size is so much smaller, so much smaller. But if you happen to share the stack space, not the stack, but the stack space, then you have to be very careful. Now, let me convince you that you can share the stack space. Preemption tells you, of course you can. Because if I'm preempting you, I'm planting my stack on top of yours, and when I'm finished running the job, I take my stack away with me. And when you resume, your stack as it was before. So I'm not interfering with you, understand? So preemption is friendly to sharing stack space. What destroys it is blocking. The previous protocol forced you, when you ask for a resource and you find it either busy or free, but with the wrong value of the system ceiling, you block. And if you block, the stack is no longer shareable because the following happens, a disaster happens, you know? This is what I explained with preemption. You are having your stack space, you are preempted, a stack of another task is planted on top of yours, that task goes and your stack continues to be as it was. So then you're happy, you didn't notice. Now what happens if there is blocking is that the task have planted, you know, the stack one on top of the other, suddenly you are blocked. And the task that you had preempted must continue running because you are giving it your priority. And of course, now the stack of this guy is on top and on the bottom. So you're now becoming the hamburger in the sandwich. And therefore, your stack space is fragmented, which causes all sorts of problems. So that's a disaster. You understand? So that, you know, this friend of mine, hopefully he would say the same of me, but never mind. This baker was a friend of mine. He said, we cannot use that protocol because that would prevent stack space sharing. And it used to be important when memory was not large for real-time systems. He said, I have a better rule, he says. And in 91, previous millennium, made a proposal and he said, look, you have to use the system ceiling differently. And instead of using the system ceiling to stop you getting a resource when you ask for it while running, use the system ceiling at your release time to decide whether you can run or not. It's like, you know, the way I would describe this, I normally do that in class to students. If I'm not a driver because I have no driving license, because I would never pass the exam myself with you know, and therefore I'm a pedestrian. And I inhibit protocols, therefore all traffic lights, you know, I switch them to red for cars. But anyway, you know what is a red wave, you know, you have a long boulevard at the time before the French invented a roundabout called one pont. And then in front of you, you want all to become green simultaneously so that you can launch your car at maximum speed. The notion of this protocol is the green wave. If you're allowed to run, you must be in a green wave. No way that any resource that you may need can be held while you run. That's the notion. So that was a clever fix. Say, use this system ceiling, but don't use it when you want a resource. Use it to decide whether your schedule. And if the system ceiling tells you you can go, it means you have a green wave in front of you. That was a nice protocol. And when I listened to it in 91, you can tell how old I am. I stood and say, applaud. Fantastic, man. This is beautiful. Not stupid. This is beautiful. I like it. And then I asked myself, can we do better? And the answer is, yes, we can do better. How can we possibly do better? What better can we do than this? And the answer is, we don't use the system ceiling. Well, wait a sec. But the system ceiling was the key to it. The system ceiling was exactly what allowed us to implement the rules. And then, you know, if you think harder in a Sherlock Holmes type of reasoning, and you have Mr. Watson next to you, say, oh, that's obvious. That's obvious. Now I see why. Well, because the system ceiling really doesn't matter. What matters is that your priority at release is such that if any resources that you want and are busy at the time prevent you from running, you don't care about the others. Now, can you see what I'm trying to say? I'm saying the situation that you don't want to be with is that you are allowed to run at your release if any of the resources that you may want during your execution are already held by tasks that you are preempting. How can you tell this without using the system ceiling? And the answer is very simple. You can, as long as the tasks holding a resource acquired during that time the priority ceiling of a resource. And done, finished. You don't need a system ceiling. You understand? The system ceiling is calculating a system level, system-wide value for all use relations of resources. We don't need that. That's clever, but you can do with less, because all that matters is the green wave. It matters to you if any of the resources that you may compete with, and therefore such that you influence their priority ceiling, are in use. So as long as a task using a resource inherits the ceiling priority of that resource, at release, you'll not be able to run because you'll have priority lower than that. Or equal, but if it is equal, you don't run anyway. Can you see what I'm saying? Hopefully so. So this is the solution. So you can do better, and that's a better. Now, time for poll. I think it's a self-evident poll, but really I want to see whether you agree with me. Let me show the poll that I would like you to consider. Of course, I made, when I was I was listening to Ted Baker when he presented his particular protocol, and I uploaded, and I was part of a group that discussed, invented, if you like, the other protocol. Therefore, I did not upload myself. Now, I would like you to say, I'm making my choice. Please make your choice of protocol after all of my telling you. And then after this, you can get 5 minutes of break after all of this tiring excursion across protocols. I want more, huh? Last time we didn't have enough voters. Ta-da, ta-da. Nice feature, this poll. You can see the trends. 30 seconds, still not enough voters. More voters, more voters. Come on, come on, come on. "45 seconds. Very many people still, pondering, say, I don't want to expose myself in case I'm saying something stupid. No, never say stupid. Come on. 51 persons responded. 15 more seconds. Tuck, 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 tuck. 11 seconds. Too many people don't want to vote. Man. 3 seconds, 2 seconds. Time's out. Let us look at the results. Who wins? Wins by some distance, my friend Ted Baker. So that's the protocol I want to upload, same as I did in 91. Some of you, surprisingly, want to use my grandmother's protocol, blocking all traffic lights in the city. And you can imagine the concert of, or what is my choice? Can you guess? I suppose you can guess. My choice is the plain ceiling priority. I don't want to spend time using the system ceiling. Is that protocol used? Not the stack-based, the plain ceiling priority. Is that protocol used? Yes, it is. And I don't tell you by whom. You get 5 minutes break and you come back, and then I tell you what language is using that priority, that protocol. 5-minute break. I'll see you here in 5 minutes. All right, 5 minutes have elapsed, to my watch at least, in my time zone. And I think it's time to resume. We'll do that slowly so that those who took a long walk across the building can come back. So this is what I said at the start of a lecture this morning that I'm skipping. In the PDF, which all you should have, and if you don't, you can go get it from the your own area of the summer school platform. There are a running example with exercises. I leave it for you to use without going through it now because it would take me too much time and I would not be able to complete the program for today. I think it's a nice example, and therefore the exercise of seeing what happens on a timeline would be illuminating. So I really recommend, if you have time and interest in these things, to look into that. But what we do now is we summarize what we know. And what we know is important. Now we have added the ability for tasks to share resources in a manner which is amenable to real-time reasoning. The cost of that is called blocking. The blocking is a duration in which, although you would be allowed to run because of your priority, you would not be allowed to run because of a resource sharing. The protocols that we're seeing in a sequence, the best one of them, allows this blocking to be upper bounded and to be pretty small. And therefore, this is acceptable in real-time systems. So now we can conclude that in real-time system, we can use aperiodic tasks by using the server that I spoke before about, and we can also use task sharing, because there are ways, intelligent ways and clever ways and interesting ways to control the blocking and make it acceptable. But once we knew the blocking, what we can do, then we simply correct the response time equation. And on the knowledge that we pay blocking only once per job, we may add this term, and this term is the maximum time that a lower priority job than you can use a resource with a ceiling priority greater than you. You calculate this value statically. Of course, you can calculate this value statically only if you know all of the tasks in your system and all of the use relations between tasks and resources. Otherwise, you cannot. Which means that real-time systems need static knowledge. It's not like a discotheque in which people can come and go and dance and go away, and you never know how many participants are there. But if you know that, then it's easy. You simply add this term, and the rest is exactly as before. Now we dive a little bit more into the implementation. So you see, I've been looking into the theory, equations, and stuff, and now we look into something which really happens under the application. And I'm not reading all of the arguments. Again, I'm skipping material, but it is in the PDF. And I concentrate on some aspects which are perhaps important to some of you, especially those of you who said yesterday in the poll, in the first poll that we had, that we have no familiarity with this topic, with real-time systems. All right, so let us, first of all, reckon with the fact that we have to use the clock. Why? Well, fundamentally because most tasks are periodic. Not all tasks are periodic, but a good number of them are periodic. So they run on a clock. Whose fault is it that most tasks are periodic? And the answer is simple. The fault is the control physicist. They want it to be so. And because you're in lower caste than them, you obey. Therefore, you need the clock. Would you, not you in person, I'm asking students, you know, when I'm in presence, and of course they don't know, how does the clock work in a processor? They have no idea, because of course in computer science you don't look at the way clock works. Clocks are very strange beasts, because fundamentally they are two adjoint registers. One register is a decrementing register, and it is decremented by the hardware at the rate of a particular device which is pulsing very rapidly. And why is this beast decrementing? It is decrementing because for a processor to read that the register is all zero is very easy. And therefore, the register, the hardware part decrements, reaches zero, and this zero is an event that the hardware can notice. And this, the hardware can use to notify the F of a fetch stage of a pipeline, saying, well, no, something happened. The clock triggered. And can you tell how much time passed from the previous trigger? Of course, yes, because that register is automatically resetting to a constant value. So it decrements in a fixed time, reaches zero, which is notified to the F of a fetch, and then again starts decrementing again. So this is a fixed time interval, which is notified to the F of the fetch. And then you have a software register attached to it, which instead increment, because that software register counts how many ticks have passed. You see? So one is decrementing, causing a tick to happen, and the other increments, counting how many ticks from the beginning of time. That's the way clock works. The software part is completely irrelevant from a real-time perspective, because we don't really tag files. We don't have files. What we care about is that some time has elapsed, and the time that matters is the one that is bounded by ticks. One tick, or a few ticks if you like. But then the important notion now is that you have this tick that arrives because the hardware tells, and then you want to attach a handling to the event, which is called an interrupt, that attached to the tick of that particular, to the alarm that was raised by that decrementing clock. Now you know why this is called interrupt. It is called interrupt because it stops the fetch stage of a pipeline. That's an interrupt. Otherwise, a processor would do fetch, decode, read, execute, write, fetch, decode, read, execute, write, forever. With an interrupt, it says, oh, I cannot fetch. I have to do something else. And what else? Handling the clock tick. To do what? What would you do in a real-time system when the clock ticks? And then the answer is, well, of course, you increment the software part of the clock. Fine. But can you do something else? And this is time for a poll question. Now that I'm giving you this initial element, you know, there is a clock, and the clock is made of these two registers, and one of these two registers decrements, and this decrement reaches zero and raises an interrupt, and this interrupt is to be handled, and this interrupt is in fact in itself periodic. I think this is time for this particular question, which forces me to display the poll. And now please try and answer this poll. And this poll is, of course, is a tricky question, you know, and it is malicious. And I'm asking, now we are talking about the scheduler. And really, please speak your heart, be honest in your answer, and say, is the scheduler a task, or is it something else? All right, answer, and let me see what your answers are. People are tactical, they don't want to answer. All right, so somebody. All right. All right. Ta-da. All So answers are coming, good. All right, still a low number, and we're 43 seconds. Come on, come on, come on. If we were in class in Fuji, you would not be able to escape this point. Huh? I would be walking around the class, and you wouldn't be able to hide. Now, 60 seconds have passed. More answers, please. We're using another 15 seconds, and then whatever it is, it is. Ta-da. Ah, people are hiding. People are hiding. 5 seconds. 5 seconds left. Dun, dun, dun. And, oh gosh, not enough answers. Let me show the results. Now, the one who says I'm lost, it's my fault. Oh gosh, there is still someone that I'm not able to persuade, you know. Say, well, you know, you're not giving me any hint about that stuff. The answer that wins, but not by a long distance, is, oh man, you placed the pole at a tactical moment. So I believe that the moment you placed it revealed the answer. So it has to do with the stick from the clock. Others say, well, come on, it's obvious there is a task that does the job. Let me start from this answer. Oh, it's clear, there is a task that does the scheduling. Because that's the most obvious answer, and it is the most obviously wrong answer. Because if there was a task doing the scheduling, who would schedule this task? Because you would have to be a recursive scheduler. You know, it would be a task that scheduled the others, and there will be something else that scheduled the task. That would have to be a task, you see? So this never ends. So it's not a task. And that's, I believe, the most disconcerting discovery for people approaching real-time systems. But the scheduler is not a task. Oh, no, I don't believe this. I want my money back. It has to be a task. Otherwise, I go away. No, it cannot be. It is not a task. It is only a procedure. A procedure. In fact, a few procedures, really, to take away from the ready queue to insert in the ready queue. And who is running the procedure? Now you begin to understand. It cannot be the application, really. Because the application is not aware of scheduling. We do it preemptively. It has to be something else. And the answer is, it's either the clock, as we have seen so far, or it is what the task does and causes a change in the ready queue. Now think of what the task can do that changes the ready queue. The task can do two things to change the ready queue. Can end the job, the end of any procedure, and therefore say, well, you go, and I take you away from the ready queue and I choose another one, if there is another one. Or the task can be blocked because they want a resource and the resource is busy. If we are not using the clever protocol, the one that I want, the one that I upload. Otherwise, no other thing, you know? So you see, scheduling occurs not because there is a task doing scheduling, but because the clock ticks and or because the ready queue is being modified by somebody going or somebody coming. Somebody comes in the ready queue only if there is a clock tick, because that's being awakened, or because you were blocked and you're no longer blocked. Okay, so you see, that's the intuition. The answer to this question is no. Fragorous no. So the scheduler is this beast. In most real-time operating systems, the scheduler is, in fact, attached to the clock, to the tick. And I consider, and in fact, we call it tick scheduling, and I consider this solution terrible. I'm not saying stupid because otherwise people feel offended. Because if I'm only doing scheduling when the clock ticks, or when the clock ticks 10 times, because when the clock ticks, it can be too short the time to acknowledge, then I'm costing. It's like polling, you know, anything happened? Anything happened? No, nothing happened. And that's really wasteful and causes problems. So this example, which I'm not elaborating on, shows that if we do tick scheduling, nasty things happen, which may lead to deadline miss even. And what the first thing you notice in this picture is that this blackish, brownish rectangular there at different sizes to symbolize the fact that the activity of the scheduler takes a variable time, and when it is all summed, the result can be nasty. So tick scheduling is easy to implement because you attach it to clock ticks, but it is not very clever because it does things with regard to scheduling when the clock says, but the clock is not the only source of scheduling events. And therefore, you are late for scheduling fundamentally. Okay, so not very nice. One more thing that we want to know. I mentioned interrupts. In any real-time system, there is certainly one interrupt handler for the clock. Is that all? Of course not. You may have other interrupts. And why do we have interrupts? As I said, because otherwise the processor, in the von Neumann style, does fetch, decode, read, execute, write forever to compute wages. And that's all it does. And you don't want that in a real-time system. So you want to listen to what happens outside, which means interrupts. Now, is handling interrupts a piece of cake? No, it's complicated. It's terribly costly, super costly. Lots of things you have to do. Now, I don't have the time, apologies for this, to elaborate on that. The slides indicate all we have to do. But fundamentally, interrupts require an activity which you all have to do at the F of the fetch, if you understand what I'm trying to say. And this is a variable duration work, because one part, which you call immediate handling, is independent of a specific source of the interrupt and allows the processor to be in a state which is not perturbed, confused, corrupted. And one part, which is called deferred, which does the things that the device raising the interrupt wanted done, and you don't want to do it in the manner of the handler, because the manner of the handler is obviously with interrupt disabled. And the duration in which you don't want to listen to other interrupt cannot be large. It must be small. Because if you don't listen to interrupt, you may have very rudimentary hardware that forgets about other interrupts. Because to have hardware that remembers other interrupt, which you call pending, that have occurred but you don't listen to, requires sophistication. So the immediate service must be short. And what do you do for the rest? The rest you defer to a task. And that task is a sporadic task. As long as you're able to bound how often that interrupt comes, or you defer job to it, then you have exactly a sporadic task. So some part you do in the handler of the interrupt with interrupts disabled. The other part, which may be longer, you do in a task, which of course is sporadic, because the only interrupt which by definition is periodic is the clock tick. All of the others are not. And those coming from the real world are certainly not periodic. How many things do you do? Oh, well, one thing which again is interesting. How can you tell what was the source of the interrupt? Well, if you have rich hardware, the hardware tells you, because it has a vector and it has bits asserted at 1 for those devices that raised an interrupt in the period in which you were not listening to them. So this is called an interrupt vector. How many processors that you use in cheap real-time embedded systems have an interrupt vector? Answer is very few. What do the others have? Nothing. They have only one single bit says interrupt has been asserted. And then how can you tell? You have to ask. You do polling. So, you're still hanging at the F of the fetch, and you have to ask, who did raise the interrupt? And you ask, front row, did you raise the interrupt? No, I didn't. Second row, did you? No, I didn't. Last row, oh yes, I was. And it was the last you ask. Okay? So all of this polling comes because the hardware is cheap and couldn't care less about real time. And during this period in which you disable the interrupt and you have to detect what was the source of it, I have to ask, who was it? Huh? Polling, terrible stuff. These are the things you do to begin serving an interrupt. Lots of them, lots of them. And you know, some are obvious, some are less obvious. For example, this one, you are stopping the pipeline, and therefore you want to clear the pipeline stage in the processor. So all that was done, gone, because you do something else entirely. No? So you do a number of things, and this takes time. This takes time. So that's why you would want to use the deferring part to a sporadic task. If you want to read more, there is something interesting to read, but it's not time to elaborate on that. And now we delve into say, oh, this blasted worst case execution time. How could we ever compute? Because remember, I mentioned earlier today, that's the only task parameter which is for the computer scientist to study. The others are given. All right, how can we study it? And this is how we analyze how this is computed. Remember, it's a worst case prediction. It has to be a value which is the largest possible demand. And again, this sounds very bad because I'm saying largest possible demand. And you know that this is worst case compute execution time, therefore would mean that the symbol is E. And as I told you that the symbol can also be the C for computation. What techniques do we have for computing this value? Well, those who are more in the theoretical part of the world say, well, of course, use abstract analysis. You reason about the properties of things, not about the real things, and you obtain a value which has algebraic properties, and this is called static WCT analysis. Others say, come on, you have a processor, you have a program, run the program on the processor and tell what happens. And this is called measurement-based. I'm taking no side for the money between which one of the two is possible. Now spend a few seconds looking at this picture. This is a very famous picture, came on an important publication that was summarizing a few years back. I'll give you a reference. What is really the state of the art in the understanding of the WCT analysis work? Now, on the horizontal axis, you have a duration of an execution. On the vertical axis, you have a frequency in which that duration can be observed ad infinitum, not during an experiment. You know, in theory, you run forever. How often do you see that duration? Well, it is not proven, but it is evident, self-evident, if you like, that the behavior, the frequency distribution of execution times of jobs have a kind of a Gaussian behavior. So you see frequently average case values, rarely enough very small values, and super rarely very long values. So it is like a Gaussian, but the most important thing is that if you want to have a value for WCT which allows for predictability, it has to be an upper bound. It cannot be lower than the actual truth. Because if it was lower, then your system would be absolutely doomed because you would not be dimensioning the right size. Now, the problem is, in theory, the actual worst case is this value, which is greater than the highest value you ever observe running for 15 years. What bound can you get? Well, guessing the right or finding the right value is, of course, very difficult, next to impossible. So you would want to have an overestimation, but how high, how big that overestimation? Well, you would like it to be tight. Because if you don't make it tight, you are in problem. Now, let me tell you this, the processors don't help you. Processors don't care about worst case. They care about average case. and they may have corner cases that are terrible, absolutely terrible. And therefore, who are you? You have no way of solving the problem. You're stuck on whatever that is that you get. And there are very few idealized processors that are amenable to having a bounded worst case. But one of the most famous ones, the acronym of that is PRET, P-R-E-T. Edward Lee is the inventor of that notion. It's very rare. It has a single implementation. It is not in mass production. So, see, it's complicated. Now, let me try and elaborate how can we do. Of course, what would be the preference? The preference would be to use abstract techniques to place yourself on this side of the problem, because if you only observe by making measurements, you risk only seeing what is visible and therefore get the wrong value. In the domain I was working before moving to the university, what did people do? They used inflation. They said, I've seen 10, let's say 27. And when I was asking, why 27? Oh, it's experience, it's engineering judgment. So, well, nice, okay. And of course, it's like following a recipe from a book, You say, a pinch of salt. Say, how much salt? You see it, it's obvious. It's just enough. So this engineering judgment, I don't trust. Perhaps you do, but I don't, especially if it comes from physicists. So what do people do? Well, let's try and see what can we do using abstract algebra. Well, it's very sophisticated, and it does two things. At one level, addresses the program structure, so that you understand what would happen in the worst case to the program logic, and determine a representation of the program, what it could execute, not so much from the function that it computes, but for using that as a basis for a cost function. And the cost function is determined by the low-level analysis, which says if you're running those instructions in that sequence on that processor, they may cost this much. So this is the technique you use. Sounds simple, it isn't. There are techniques and tools to do it. For example, this slide is coming from a group in Toulouse that have developed a non-commercial tool called Ottawa that does this. And again, it assembles the pieces. The most important part that resolves these, if you like, abstract equations for finding the worst case execution time, assuming that you have acquired all knowledge about the program and its structure, is constructing an equation which you solve by linear programming, integer linear programming, which represents a set of constraints over your program structure as a cost function whose unit of cost is the cost of an instruction in that sequence of the processor. So again, this is, you read it for yourself after this lecture. It's a way, from an example, to try and make sense. So you construct this control flow graph, CFG, you construct by identifying blocks of execution, which are called basic blocks. A basic block is the the largest sequence of object code execution that has a single point of entry and a single point of exit. This is a basic block. And then it jumps somewhere. Therefore, the edge here is a jump from a basic block to another one. So you construct this by looking at the program, the source, and the object code. And then by knowing properties of your program, you decide what is the weight of the edges, because that is a cost. And then you represent all of the constraints you know in the program. For example, this is a loop, and it means that you're entering here and you're crossing there up to this many times, and therefore there must be so. And you find by linear programming what is the set of values that maximize these constraints, that sometimes are qualities and sometimes are constraints. So you do this and all is fine, except that high-level analysis that construct this control flow graph is full of uncertainties. Why? Why? Because the arcs, for example, often depend on input data, and you don't know the input data. Sensor No, sensing, computing, actuating. What value will you sense? I don't know. I don't know. How can I decide if I go left or right? If you ask me, I always go left. But if you ask reality, you never know. So you don't know. Often you don't. Therefore, you have to guess. And what you guess? I'm going the path that has the highest costs. But that path may be infeasible. You can never be in that situation. If you're in that situation, it will be very severely anomalous. And then you have a thing that you don't want to have in a real-time system, which is a while loop. This would be a time for having a poll, but it is too complex to build. Would you people use while loops in a real-time system? A while as opposed to a for loop? Please don't, because a while loop has no bound. Of course, the exit condition is while something, while the sky is blue. But give me the worst case for when you leave the loop, when the condition is while the sky is blue. You don't know. It can be forever. With a for loop, for says for from 1 to 177. I know it's the bound is 177. And then the last difficulty comes with, one of the inheritances of C and C++ for that matter, and it is pointers. Now I am calling a pointer. Do I know what I'm calling into? Of course I don't, because I would have to use very complex analysis to tell where the pointer resolves to. And then once I know, I can build the control flow graph. So are pointers, dynamic calls for pointers, a nice thing to have in a real-time system? Well, no, they are not. They make life much complicated. So it's complex. What do you do when you don't know? You ask the user, the programmer. And does the programmer tell you the truth? Of course, no, they don't. They have no idea. And often the programmer is no longer there. And therefore you don't know. So this is a story that is really true. The author of the initial version of the slide was an older student that I supervised as a PhD. In his part of his research, he went to an important company that was building very sophisticated real-time systems, and he was there to investigate how we could improve some of the techniques for WCT analysis. And of course, he was looking at a very complex piece of software. And one of the things he did as soon as he arrived there, he was asking, where is the author of this software? And people were looking at their shoes and said, where is the author? I said, well, the author is no longer here. Does anybody know about this software? And the answer was no, don't touch it. So that software was object code only, can you imagine? And nobody knew about it. Yeah? So how can you derive some of this information from that software? You cannot. So this is complicated. The low-level analysis, remember, does determine the cost of the edges, because an edge costs as much as crossing the basic block, meaning executing those instructions on the particular processor in that particular order. Do you know this about, do you know this information for processors? The answer is you don't, because hardware nowadays, processor hardware is complicated, it's full of, restricted information, and it's full of very funny, strange effects. Some of these effects are in fact anomalies. Others are, Now, two things I want to elaborate with you and show. One is the cache. The cache is a very complex beast from a real-time system perspective. And the other is the principle of this analysis, which may be really broken by some hardware oddity, if you like. So the cache. The cache is there for average case. So the basic notion of the functioning of the cache, I am behaving, making average case assumptions. But we don't live with those. In a real-time system, we work on totally different perspectives and presumptions. So we have to understand how the cache works. And the cache works according to different methods that I'm briefly recalling to you. But then not only this, the cache, if you like, as a behavior, and we have to determine what is the behavior of that cache in the worst case for a program. And you understand the pessimism that this may give, pessimism that may be terrible. So the principle of a cache is that you fit something there because you believe, when you means the execution and the way the cache functions, you expect that by placing that stuff there helps the program locally. The choice of what to put in the cache and where to place it is in fact called associativity. So you have different styles of associativity. One extreme is that you place anything that from the RAM that has to go to the cache, and you place it anywhere you like. Of course, if you do it, you have maximum freedom, but it's very difficult for you to tell where the things is when you look for it. So, and because it is the hardware that I have to tell, the hardware, no hardware that I know implements full associativity. So it gives you always a smaller choice of where you can place stuff. So if you had freedom to place stuff anywhere, you'd be happy. In placing, you had a harder time in retrieving. The extreme alternative is that you only have one position. This is called direct mapping. Any location in RAM has only one possible position in the cache. Is this good news? No, it's not. And this is very bad news for a very simple reason. The cache is very small in comparison to the RAM. So when I'm saying that you have a fixed position, it's not your fixed position, but lots of other RAM addresses have exactly the same position as you. So you have a cache conflict, maximum cache conflict, when you have direct mapping. Because the cache is divided in smaller blocks called lines, and the RAM is in fact seen as a succession of such lines. And therefore, you have a modularity. Now, if you are in the 7th position in that line, you all collide in the 7th position in the cache. So when you have collision, if you are in, somebody is out, and somebody is to come in, and you have to go out. And this is bad news. So what is the choice? Ideal choice, which most caches use today, is called n-way set associative. They give you some choice in order to reduce the conflict, but it is not full choice as it would be in fully associative. However, now this is a nice picture, not mine, too nice to be mine, that gives you an interpretation using a bookshelf to understand how these things work. But what is the message? The message here is that in a cache, the problem is that to answer the question, now that I'm executing this instruction, will I retrieve my data, and perhaps even the instruction, in the cache or not, depends on history. And can you tell history? The answer, no, you can't, because you're not making measurement-based analysis. You have to make worst-case analysis statically, and therefore you have to make a complex reasoning that says, I cannot tell history, but I have to upper bound the history. So that when I'm telling the outcome, yes, you'll find it, or you will not find it, you have to go to memory, is an upper bounding worst case. And I think you can sense that this can be terribly, terribly pessimistic. There is one more thing in which the hardware does not help you. The hardware can be very nasty on you. And that's the way it works. I described the analysis, the static analysis, by telling there is a high-level part in which I construct the control flow graph, and a low-level part in which I'm giving the cost to the control flow graph, the edges across the various nodes, which are basic blocks. Fundamentally, this low-level versus high-level logic assumes that when you are looking for the worst case locally, you will obtain a worst case globally. This would sound like obvious. It should be so. Can we say this is true for all processor hardware, that when you're looking into a local worst case on a particular resource, on the cache, on the bus, on any particular user or register or something, this will always cause or incur a worst case globally in the execution of a job crossing on that resource? And the answer is no, no, no. You may have a situation in which you are when you calculate in the low-level analysis a worst case, But worst case does not lead to a worst case global, but leads to a best case, or not a worst, if you like, which is really creating a thing that we call timing anomaly, the fear of this analysis. You know? What's the logic of that? Very simple, because time is running, and there is more that I want to tell before we end the lecture. Now, imagine that we have resources. These are hardware resources, you know? A bus arbiter, a cache line, any other thing that needs to be shared. And these resources have requests that have to be served. Some requests are independent, others are dependent. So when there is an arrow going down, it says first you have to do A and then you have to do B. Or you have to do first C and then you have to do D. But C and B are independent of one another. Similarly, D and C. So these groups arrive at their resource however they arrive. But you have to make an analysis. And if scheduling on the resource requests is so-called opportunistic, that is to say, every resource decides on its own, then you see what happens. Situation here is that there is a request made to resource 1, and the request is A, and A is lucky. It's served very rapidly, which means that B is enabled very rapidly. And B precedes C. But C precedes D on the other resource. And E comes and gosh, I have to wait until D finishes. So a best situation here leads to this sequence end. Now let's look at what happens if the action, the execution of A on resource 1 goes wrong, takes longer, much longer. What happens? Oh, it happens something interesting. C goes first because B is to wait until A finishes. But if C goes first, D goes earlier. And D going earlier allows E to end earlier, which means a worst case locally has given rise to not a worst case globally. Very bad news. Very bad news. Now, people studied whether there was a common origin to this so-called timing anomaly. There is only a conjecture that as to what explains it. There is no proof. This conjecture is that this happens when resources decide on their own logic what to serve. And they are greedy. So I have a request, I serve it regardless. And this is, philosophically, it makes sense. If you want to know in a proportion how many processor hardware contains timing anomalies, the answer is a very high proportion. Is that included intentionally? Of course not. Of course not. It's not intentional. It's not by design. And the presence of timing anomalies is increasing because hardware is designed by software. You write software to produce hardware. And unfortunately, who writes software doesn't know software, which are my hardware engineer friends. So it's a very complex world there. So can we use static analysis for WCT? The answer is, of course, there are very super fantastic tools. One is in particular called AIT by a company in Germany called Absinthe, without an H. It's not like this, spirit. Absinthe without an H, from Saarland. It's really a super nice tool, very powerful, but adapting it to a specific processor is a massive effort and a massive cost. And it also leads to some uncertainty because you cannot trust often the hardware documentation. What is the alternative? The alternative is called hybrid. You don't want to measure only because if you measure, you're fooled by what you see. You have to measure and use knowledge, abstract knowledge, and you put them together intelligently. Now, there is a tool in England, and the company there is called Rapita, now is part of a larger corporation. They were very sorry about Brexit because they feel very much European, but Boris Johnson told them, come on, you belong here. And this tool is Rapitime, and it does hybrid analysis. It's really the opposite of the AIT by Absinthe in that respect. There is an interesting thing that I may want to mention in the last few minutes. which removes some of the uncertainties. I mentioned the cache, and I told you that cache is not the only one hardware resource which is state dependent. And state is a complex thing, because if you get the state wrong, you make a wrong prediction. So what do you want to, what would be a way of solving the problem of not depending on the state? Make the cache behavior not state dependent. Can you make the cache behavior not state dependent? And if you make it, are you kind of throwing away all of the value of the cache? The answer is yes, we can. And the solution, this is Obama style, the solution is called probabilistic operation and probability analysis. It's interesting because if you choose what to evict from a cache on the basis of a random choice, true random choice, you don't depend on history, you depend on probabilities. Probabilities you can calculate. There is mathematics to do that. So that's an interesting avenue. You know that probabilistic behavior, if you like, makes the worst case no longer state dependent, which is pretty nice. And in fact, this randomic behavior in certain choices, not in the function that you calculate, is one of the key measures of defeating cyber attacks, because you are having a behavior which is erratic to the outside observer. They don't know what it means, and therefore they can hardly infer. So the same notion is usable in the other sense. So the global picture for this hybrid analysis is that you take the real program, you take the real hardware, you need devices to obtain execution traces that are non-intrusive. So that's a complicated thing to do, but it can be done. And you use abstract knowledge to reason on the control flow graph with knowledge of the actual execution, which is what you need when the hardware is unclear or uncertain. And then you reason about it and you fight the problem of not being optimistic, because having an optimistic worst case is nonsense. And having a terribly pessimistic worst case, as I was telling you, engineering judgment that said, what I've seen, which is called high watermark. What I've seen is 100, make it 270 is of course not sustainable, regardless of who says so. When I was young and I was working in that organization, of course I was very timid working around this table of very expert engineers, but it was obvious when one said, make it 270, there is no rationale. And you ask, why? And this guy says, because I've been working in this place for 20 years and I've seen never longer than 270. Is that an answer? I'm sorry, it's not an answer. So that's really a big problem. Anyway, that's the end, and I'm pleased that it's just about the time I wanted to be, perhaps a little earlier when I marked myself to finish at 3:20, and it is 3:18. Good. We can have 2 minutes if you still have energy, or perhaps 7 minutes, even if you have even more energy, to fire questions. Yesterday, I didn't really answer all of them, and I didn't even take notice of what I did answer. But if you have questions to answer, if you're still there awake in your time zone, or if your mind is still functioning, I'll be up to have questions that you may have, as long as you use the question and answer bar of Zoom. Otherwise, I have to consider that you're happy and satisfied and you don't want your money back. All right, questions are not coming. Of course, it takes time for you to think of questions, but never mind. And you know that in webinars, the most horrible situation is silence. So the speaker waiting for something to happen, but that not happening, and therefore silence. And where people say, oh, what happens? I lost audio. I'm still connected. What happened? So we don't want to have silence. That's why I'm blathering. But I don't have to, because if you don't have any questions to ask at this time, I should assume that you're happy. All right, one question from Jasmine. Jasmine is always asking questions, which is fine. Let's see. the question by Jasmine is not very clear, so I don't know whether I can answer. The question is, I think you can read it. I don't know if you can, perhaps you can. This would depend on the Zoom setting. Did you consider non-blocking synchronization and its influence on worst case execution? This is a very sophisticated and interesting question. Non-blocking synchronization, you know what that means? Let me elaborate briefly on what that means. So far, I've been telling you that in order for tasks to share values, data for collaboration, you need to have a mechanism that stops one task from preempting the resource of another, share with another task, which causes blocking. Is blocking nice? No, it's not, because it's a big waste of time. So this is where there is an interest in non-blocking synchronization. That is to say, having executions. You may have known of an instruction which is called test and set, at least in books. It is not really called test and set in real hardware, in which you are trying to see spinning around a variable to say whether I can go or not. So this is possible. We'll speak about that in multi-core processors, which is what we're going to talk about tomorrow, which is a teaser if you like. All right. I believe that we can be done. Bye-bye, everyone, for today, and hopefully you're back tomorrow with lecture 3, in which we see the real heart of this intended lecture, multi-core processors and, in fact, mixed criticality systems. Bye-bye.